Have you ever wondered why a steaming cup of coffee fills the room with its aroma, or why water boils faster on a mountain top? The answer lies in an important concept in chemistry and physics: vapor pressure. In this video, we shall explore what vapor pressure is, the factors that affect it, and its everyday applications. Vapor pressure is the pressure exerted by the vapor of a liquid or solid in equilibrium with its liquid or solid phase in a closed system. But what does this really mean? Let us break it down. Imagine you have a liquid in a sealed container. Some of the molecules at the surface of the liquid have enough energy to break free from the liquid and become vapor. This process is called evaporation. At the same time, vapor molecules lose energy and return to the liquid phase, a process known as condensation. Initially, evaporation happens faster than condensation, so more molecules enter the vapor phase. But as the number of vapor molecules increases, the rate of condensation also increases. Eventually, the rates of evaporation and condensation become equal. This state is called dynamic equilibrium. The pressure exerted by the vapor at this point is known as the vapor pressure. This equilibrium is dynamic because molecules are constantly moving between the liquid and the vapor phases. It is important to note that vapor pressure depends on the temperature and the properties of the liquid, which we will explore further. Now let us talk about the factors that influence vapor pressure. First, the nature of the liquid. Different liquids have varying strengths of intermolecular forces. For example, water molecules are held together by hydrogen bonds, a strong intermolecular force. This means fewer molecules can escape into the vapor phase, resulting in lower vapor pressure. Alcohol, on the other hand, has weaker intermolecular forces, making it evaporate more easily and giving it a higher vapor pressure. The second major factor is temperature. As temperature increases, the molecules within a liquid gain more kinetic energy. This allows more molecules to overcome the intermolecular forces and escape into the vapor phase. Consequently, the vapor pressure increases. This relationship is exponential as shown in the graph. To better understand this, imagine heating a liquid in a closed container. As the temperature rises, you will notice more vapor forming above the liquid. This demonstrates how vapor pressure rises with temperature. Finally, let us touch on the role of external pressure. While external pressure does not directly change the equilibrium vapor pressure, it affects a phenomena like boiling. Boiling occurs when the vapor pressure equals the atmospheric pressure. Lower external pressures, like at high altitudes, mean a liquid can boil at a lower temperature. Understanding these factors help us predict how liquids behave under different conditions, from laboratory experiments to real-world scenarios. One key application of vapor pressure is understanding boiling. Boiling occurs when a liquid vapor pressure equals the atmospheric pressure. At high altitudes, where atmospheric pressure is lower, water boils at a lower temperature. That is why pasta takes longer to cook on a mountain. Conversely, in a pressure cooker, the atmospheric pressure is artificially increased, raising the boiling point and cooking food faster. Another everyday example is carbonated drinks. The pressure inside a sealed soda can keep carbon dioxide dissolved in the liquid. When you open the can, the pressure drops and the gas escapes as bubbles. This principle is also why soda tastes flat if left open. The gas escapes until equilibrium is reached. Vapor pressure is also critical in industrial applications. For example, it determines how easily fuels like gasoline evaporate. Higher vapor pressure fuels evaporate quickly, aiding combustion in engines but requiring careful storage to prevent vapor loss and hazards. Finally, vapor pressure is essential in medicine. Volatile anesthetics rely on their high vapor pressures to deliver precise concentrations of the anesthetic gas to patients during surgery. These diverse examples highlight the practical importance of understanding vapor pressure in both daily life and specialized fields. Now let us bring the concept of vapor pressure to life with an experiment. Here we have a beaker of water being heated in a closed system connected to a manometer. The manometer will measure the pressure exerted by the vapor as the temperature changes. As we gradually heat the water, you will notice more water molecules gaining energy and escaping into the vapor phase. This increase in vapor molecules raises the vapor pressure, which is indicated by the rising level on the manometer. This experiment highlights the direct relationship between temperature and vapor pressure. The higher the temperature, the greater the kinetic energy of the molecules and consequently the higher the vapor pressure. By observing this process, we can better understand why liquids boil at specific temperatures depending on the atmospheric pressure. For instance, at sea level, where atmospheric pressure is higher, water boils at 100 degrees Celsius, but at higher altitudes where atmospheric pressure is lower, boiling occurs at a lower temperature. This demonstration clearly illustrates the connection between vapor pressure, temperature, and external pressure, tying together the theoretical and practical aspects of this phenomena. To recap, vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid or solid phase. It depends on the nature of the liquid and temperature. Understanding vapor pressure helps us explain everyday phenomena from boiling water to soda fizz and plays a crucial role in industrial process. Next time you see vapor rising from a hot cup of coffee, you will know the science behind it. Thanks for watching and see you in the next video.